Okay, back again. All right. So that's essentially where it's at with regard to the atom, right? We take what the model gives us and we work with it, but it's not necessarily the end of the story, right? Isotopes, we kind of talked about already, right? Isotopes are just different versions of atoms that have more neutrons in the nucleus, okay? Now, some isotopes are what we call stable, meaning they're good the way they are, okay? But some isotopes of elements are unstable and they give off energy because they have so much energy packed into them. And the energy can be things like it could spit out electrons, we call those beta particles. It can give off radiation like X-rays or gamma rays. And sometimes when that happens, it undergoes a process called decay, and it actually turns from one element into another. Okay, so this breaks the rule. It says, you know, once you've defined what the element is, that's it, right? And the reason this breaks the rule is that because in some kinds of radioactive decay, we change the number of protons in the nucleus, and that changes the identity of the element. Okay, you might say, great, what does that do for me on a day-to-day basis? Well, because of this, right, we can use that energy if those isotopes are contained inside a molecule to ask questions about where that molecule goes in a living system, or we can use this energy to look inside living systems. Okay, you all heard of X-rays, right? You maybe have had X-rays. X-rays are a type of electromagnetic energy that are given off by radioactive isotopes, and that energy can pass through soft tissue, no sweat, but it can't pass through stuff like bone. Well, when it passes right through soft tissue and it hits photographic film, it exposes it, turns it black, right? And if it doesn't hit the film stays white. So when you develop the film, you get a way to look at the bones inside the body without literally having to cut you open and look. So we can use this to diagnose things like fractures, okay? How else can we use this? Well, we can use radioactive molecules to ask questions about, let's say, whether your digestive system is working, okay? Sometimes they'll do what's called a barium series. And they'll have you swallow this nasty Pepto-Bismol-like milkshake that's got radioactive barium in it, and it'll coat your digestive tract all the way from your mouth to your anus, and then it'll give off energy that we can detect, again, using things like film or a detector, and we can ask questions about whether you've got a leak or a blockage or a twist in the pipe going from one end to the other, okay? We also use contrast dyes that have radioactive isotopes in them to ask questions about are there broken blood vessels, say in your brain, or is there a problem with the fluid flow through the kidney, okay? And we do that without having to actually cut you open and look, all right? So it's pretty handy, right? That's why it's important. However, it's dangerous, right? We call this kind of radiation ionizing radiation because when it smacks into another atom, it can remove charged particles like electrons and stuff. And that can ionize whatever it hits, and that can damage it, okay? So that's why we reduce our exposure to things like X-rays and gamma rays and any other type of isotope that can penetrate soft tissue, okay? Essentially, with electromagnetic radiation, the smaller the wavelength, the higher the energy content, which means the deeper that energy can go in you. And so when you're talking about stuff like X-rays, you're talking about a very small wavelength, okay? So those are radioisotopes, right? They decay. They can spit out alpha particles, which are helium nuclei, okay, which would be essentially 2 electrons and 2 neutrons. They can spit out beta particles, which are electrons, and they can kick out gamma rays, okay, depending on the type of radioactive isotope. right? Isotopes have both a physical and a biological half-life. The physical half-life is the time for 50% of that radioisotope to turn into something that's not radioactive anymore, okay? And that can be from a few hours to thousands of years, okay? And the biological half-life is how long it takes something radioactive, or sometimes we call that something hot, to get out of your body, okay? And that's a combination of the physical half-life and the ability of your kidneys and your digestive system to clear the material that you've ingested or that's been injected into you, or that you've inhaled, let's say, okay? All right. Thyroid gland, okay, is one of the ways we can use radioisotopes to visualize problems in the body. Medical imaging basically uses radioactivity to visualize soft tissue in the body. Iodine is used in the thyroid gland to make a hormone called thyroxine, which controls your metabolic rate, which is the speed with which you burn your body fat. All right. The thyroid gland, if you apply radioactive iodine to it, will get darker in areas where less radioactive iodine is taken up, and lighter where it is taken up, because the areas that are taking up the hot iodine are going to be spitting out beta particles and exposing either the detector or the film, okay? And that can help us locate on the thyroid gland a problem area, like maybe an area that's cancerous. Okay? We can also use radiation to destroy cancer tissue. I'm sure you've heard of radiation therapy, right? And basically what you're doing there is you're trying to cook the cancer tissue so that it can no longer function, right? And the reason that it works is because when cells are rapidly dividing, like cancer cells do, they're more likely to essentially damage themselves when they're hit with radiation, because they're busy building new molecules and the radiation blows all that stuff apart, okay? So we've talked about the periodic table. We've talked about the valence shell, right? We've talked about those numbers on the periodic table and what they mean. We talked about that last column of elements, the noble gases, right? And what makes them do their thing, right? Organization of the periodic table by valence lines shown here, right? Notice we skipped all this stuff in the middle. The dotted line represents what we call the transition metals, right? We jumped all the way over back to the A groups. The transition metals are the B groups. The staircase, remember from the other picture of the table, is going to go right through here, right, on down. So these are the non-metals, right, and these are the metals. Okay? It's just an abbreviated look at the periodic table. Okay. All right. A chemical compound is just a combination of elements, two or more elements, in a fixed ratio, and they're held together by chemical bonds. They can either be ionic compounds or they can be covalent compounds. Ionic compounds are held together by ionic bonds. Covalent are held together by covalent bonds. An ion is nothing more than an atom that's either gained or lost an electron. So if an atom loses an electron, we refer to it as a cation, okay? For instance, if potassium loses an electron, it becomes a potassium cation, positive charge. I remember that because the T in cation looks like a positive sign. And then if it gains an electron, it's called an anion, okay? But why do we care about ions? We care about ions because in the body, right, ions can move from one location to another, and that is current. That's a form of electrical energy, okay? And the cells in our bodies do that in order to do work. So it's kind of like having electrical energy for things like muscles to contract, or for nerves to do their job, or for the other cells in our body to do things like transport stuff across their membranes, okay? So when we talk about the formation of ions that can occur when you throw an ionic compound into a solution, like into water, okay? And it can also occur in the formation of things that are called salts, okay? Where the cations and the anions kind of hug each other and form a crystal, okay? So when we talk about generating ionic bonds, all right, let's take the example of sodium chloride, all right? Sodium chloride is a salt, okay? And it forms from sodium metal reacting with chlorine atoms, okay? Now, a chlorine atom has 7 electrons in its outer shell, which means it can pick up 1 to complete the shell. Sodium has 1 electron in its outer shell, and the easiest thing for it to do is to punt that electron over to chlorine, and then the shell underneath it is complete, okay? So even though this results in both of the atoms now picking up a charge, they're stable, okay, because their outer shells are filled up. Now, when that happens, we change the chemical properties of both, right? Sodium metal, if I were to bring it into school, is extremely dangerous. It would burst into flames if I exposed it to open air, right? And it explodes when you throw it into water. It reacts violently. It's very dangerous. Chlorine is a powerful corrosive agent. I don't know if you've ever been around a pool when it's being chlorinated, but you'll bleach your clothes and your skin and your eyes, and it's extremely unpleasant, okay? But when we react the two together, you make sodium chloride. Well, what is that? That's table salt. That's what you put on your French fries. So why can you eat sodium chloride, but you can't get near stuff like sodium or chlorine? Well, because you've changed where the atoms are located, or where the electrons are located, and so you've changed the chemical properties of the atoms in the compound, okay? And notice how they hug each other. They hug each other by having the positives and the negatives interspersed. And the reason for that is that that's the low energy state, okay? So in the low energy state, what we're talking about is a way to arrange those parts of the system in a way that it doesn't take a lot of effort to maintain, okay? If I tried to force all the positive charges to one side of the cube and all the negatives to another side, I could do that, but it would take considerable energy because the similar charges would push off each other, okay? So another example of the second law of thermodynamics, okay? In covalent bonding, what happens is that instead of having one atom, the metal, donate electrons to the non-metal and form ions that hug each other because of opposite charges being formed, we have a pair of electrons being shared between 2 non-metals, okay? So we can call these covalent compounds, and covalent bonds are very strong, okay? We share electrons between atoms of 2 or more different elements, okay? Examples include carbon dioxide, water, oxygen molecules, and so on, okay? When we write out a molecular formula, we always have the symbol of the atoms in the compound, and then what we call a subscript, which is this little number down here, indicating the number of atoms of that type that are in the compound. So in carbonic acid, there are 2 hydrogens, 1 carbon, and 3 oxygen atoms, okay? Now, how they're connected to each other is a little different. How they're connected to each other we see with what's called the structural formula, where we get the number and the kind of atoms and the arrangement. For instance, if we were to do the structural formula of carbon dioxide, it would look like this, okay? That's CO2. And so sometimes you can get atoms that can come together and have the same molecular formula, but they're going to have a different arrangement of the atoms, and those are called isomers of each other, okay? An example would be glucose and galactose and fructose, right? They're all C6H12O6, but the atoms are connected to each other in a different way, okay? Now, what I want you to notice about these drawings, okay, is that they're kind of not totally accurate in a way, okay? By looking at these drawings, you would think that the glucose, galactose, and fructose are all flat like a pancake, and they're not, okay? They are, in fact, shaped more like, in the case of glucose and galactose, um, an easy chair, right, with a footrest and a headrest, okay? Um, the headrest of the easy chair would be this part of the ring kind of popping up, and then the footrest would be this part of the ring flipping down, and then sometimes they'll flip the other way, okay? So this has three-dimensionality to it, not just width and depth, okay? But it has three dimensions to it, all right? Same with galactose over here. Fructose would look more like just a regular chair with this part sitting up and then these parts being where you'd sit, okay? So the reason for those shapes, all right, is because in a carbon-containing compound, when you connect it to other atoms, you want to arrange the other atoms in a way that they're not too close to each other, because if they're too close to each other, they'll push on each other, and that takes more energy to maintain, okay? So when carbon is bound to 4 other atoms, all right, it actually takes on what's called a tetrahedral shape. Now, what is that? Well, if the carbon is the middle, okay, 3 of the other atoms would sit like the legs of a 3-legged stool underneath it, and then the other atom would be above it like a little post, okay? And they would all be evenly spaced apart. If carbon is bound to 3 other atoms, then it's flat like a pancake, okay? And then if it's bound to 2 other atoms, it's linear like in carbon dioxide. And those are all shapes that reduce interactions between the atoms that are connected, okay? So we've talked about covalent bonds, right? The atoms share the electrons. Equal sharing occurs between carbon and hydrogen, or between identical nonmetals, okay? And unequal sharing occurs every other time, all right? So some of the commonly utilized covalently bonded compounds in the body are going to be a combination of carbon and or hydrogen, oxygen, and nitrogen, okay? And remember that the reason for carbon being in the place that it occupies is because of, again, its ability to form rings and chains with itself, all right? So when we look at the formation of these chemical bonds, we have to consider what's going on in the outer shell, all right? So the number of covalent atoms or covalent bonds an atom can form is directly related to the number of electrons that are already there, okay? Carbon with 4 electrons in its outer shell can form 4 covalent bonds, because that results in a pickup of 4 more electrons, making a total of 8. And that's a happy carbon atom, okay? Oxygen, which has a total of 6, can form 2 covalent bonds, all right? And nitrogen with a total of 5 can form 3 covalent bonds, okay? So those are just a few examples, all right? A single covalent bond shares 1 pair of electrons. A double covalent bond between 2 elements shares 2 pairs, and a triple shares 3 pairs. There's no such thing as a quadruple covalent bond, and that's because of geometry, okay? Beyond the scope of this course, basically, okay? So there's some examples of single, double, and triple covalent bonds, okay? Now, how do you tell that everything's good? Well, you do your bookkeeping, right? You ask the question, for each atom in the compound or the molecule, are the outer shells filled up? So let's look at this hydrogen atom. 2, we're good. How about this hydrogen atom? 2, we're good. Well, you might be saying, well, we counted those twice. We're allowed to, because they're shared between the 2 atoms, okay? So that's a stable compound, hydrogen gas. Full outer shells, everybody's happy, right? How about oxygen? 2, 4, 6, 8. Cool. How about over here? 2, 4, 6, 8. We're cool, okay? That's an example of what's called the octet rule, right? Once we get to 8 in the outer shell, certain elements in the table are chemically stable, specifically the ones that are important in life processes, okay? And then over here, here's nitrogen, right? 2, 4, 6, 8. We're good. 2, 4, sorry, 2, 4, 6, 8. We're good over here. Okay. This pair member is in a different shell. That's a triple bond. That's the most powerful, right? And that's nitrogen gas. And you can also form bonds between different elements, right? Carbon and hydrogen happen to form a nonpolar covalent bond. That's methane right there. All right. Again, if you do the bookkeeping, each hydrogen atom has 2 in its outer shell, and carbon here has 2, 4, 6, 8. So everybody's happy, right? Over here, CO2, right? Well, let's look at oxygen. 2, 4, 6, 8. That oxygen's happy. 2, 4, 6, 8. That oxygen's happy. How about carbon? 2, 4, 6, 8. Everybody's happy, okay? With 8 in that second shell, everybody's stable, stable compound, right? This is ethanol, right? And again, if you do the bookkeeping, you'll see that all the hydrogens and all the carbons, the oxygens, all have filled outer shells, okay? Which means they're stable, which means it's a stable compound, which means we don't do anything to it. It'll just hang that way and it'll be fine, all right? All right. Sometimes we have to draw carbon-containing compounds using different representations, okay? You can see some examples in each of these boxes, all right? Remember I told you that carbon can form rings and chains with itself, and that's where you get these different shapes of compounds, right? We've got straight chain, right? We've got branch chains. We've got rings. We can have rings and chains, rings and branch chains. We can have almost any combination you can think of. Now notice you may have some double bonds, right? You might in some cases have some triple bonds, okay? And those can occur in the hydrocarbons as well, right? What you're looking at mostly here, with mostly carbon and hydrogen, are molecules that are almost exclusively nonpolar, which means that if you looked at their surface, the electrons would be distributed evenly. And that means that they don't have a collection of charge at one end or the other. And what that means for them chemically is that they like to interact with each other. They like to be with their buddies, okay? So they'll stay away from stuff that has what we call polar covalent bonds, things like water, for instance. We've talked about electronegativity. That's just the tendency of the atoms in the nonmetals that are to the right of carbon to pull electrons towards them if they participate in a covalent bond. And what that does is it creates a covalent bond that has a negative and a positive end to it, right? So why is that important? Well, if you find electronegative atoms in an organic compound, a carbon-containing compound, that means that that molecule, at least in that area, is going to have a separation of charge, which means that part of the molecule is going to be polar. And what that means is that part of the molecule is going to interact with other polar molecules by making the charges on one interact with the opposite charges on another molecule, okay? So again, right, the common statement for that type of interaction is like dissolves like, okay? Similar molecules like to get with each other, okay? So covalent bonds can be nonpolar, meaning even sharing between the two atoms participating in the bond, and nonpolar means that they're unevenly shared, okay? So if we talk about electronegativity for the common elements that make up organic molecules, hydrogen is the least electronegative, carbon's in the middle, and nitrogen and oxygen are both more electronegative, okay? So the more electronegative atom pulls the electrons in a covalent bond towards it, the less electronegative atom tends to spend less time with the electrons in it, and so it gets a partial positive charge, okay? We use the Greek letter delta to indicate that, okay? And the result is that that region of the molecule is going to be more likely to interact with things that are similar chemically, okay? So How do we use these rules to help us out? Well, if a covalent bond exists between identical elements, it's going to be nonpolar. Or if it exists between carbon and hydrogen, it's going to be nonpolar. A polar covalent bond will be between any other combination, okay? There are some nonpolar molecules that have polar covalent bonds, but because of the arrangement of those bonds, the pull across the molecule cancels out an unequal distribution of charge. And one example of that is carbon dioxide, with the carbon in the middle and the oxygens on either side pulling equally, okay? And the result is that the molecule is nonpolar, but there are bonds in there that are polar, okay? Some molecules have regions that have different properties to them, okay? You can have amphiphatic molecules that have nonpolar regions and polar or charged regions, okay? An example here would be a triglyceride with a polar region up here because of the oxygens and a nonpolar region here because it's all carbon and hydrogen. In a phospholipid, you've got polar regions, you've got charged regions here in green, and you've got nonpolar regions here in yellow, okay? And so that's an unusual molecule because some of it is going to interact more readily with something polar like water, and the other end is going to interact with molecules more like itself, okay? And there's an example of a carbohydrate, and the whole thing is polar because of all of the electronegative atoms in it, okay? So weak chemical interactions between molecules are called intermolecular interactions, and the most common example are hydrogen bonds, okay? What hydrogen bonds are weak interactions between the hydrogen in a polar covalent bond on one molecule and a electronegative atom on another molecule. An example of hydrogen bonding with glucose is shown here. The H2O of water down here is such that the oxygen has a partial negative charge, the hydrogens have a partial positive charge, and the result of that is that you have a polar solvent, okay? Well, when you throw sugar in there, what happens? The oxygens of the water molecules are going to seek out the hydrogens on the OH groups on the glucose molecule. That will cause a crystal of glucose to come apart, all right? And the individual glucose molecules surrounded by water will be what are called solvated, which means they'll be in solution and they'll stay that way, okay? Other types of forces include van der Waals forces, which are nonpolar molecule interactions where you have brief, uneven distribution of electrons causing the nonpolar molecules to more easily associate, and hydrophobic interactions where nonpolar molecules squeeze out anything that's polar by associating with each other, okay? Water, as we've talked about, is a polar molecule with 2 hydrogens and 1 oxygen. Again, if you look at the structure, you can see that everybody's happy, right? Hydrogen 2, oxygen 8, okay? In a water molecule in solution, what you see is an arrangement of water molecules so that the partial positives of one water molecule associate with the partial negatives of another. And then as the molecules flow past each other, they flip and flop in order to maintain that distribution, okay? Well, we know that water exists as both a solid and a liquid and a gas, all right? Well, we can understand the interactions in a gas and a liquid, right? Because there's movement there. And so we can flip and flop in order to have that hydrogen bonding take place. But when we're a solid, what do? Well, we maintain those interactions, that hydrogen bonding, but that creates more space between the atoms in solid water, ice, than in liquid water. And that results in a loss of density, right? There are fewer water molecules per volume of ice than there are in liquid water, and that's why ice floats in water, okay? That's why water expands when it freezes, okay? Water is critical to life because it participates in and is produced by chemical reactions. It's a liquid, so it promotes movement, and movement has to exist for chemical reactions to happen. Otherwise, there will be no collisions to make and break chemical bonds. And it cushions and lubricates and excretes waste, and it dissolves a lot of stuff, okay? Um, because it's a polar solvent, anything charged or polar will dissolve in it. And that means that a lot of chemistry can go on there, and that's why it gets the nickname, the universal solvent, right? Because it has hydrogen bonding, it has cohesion and surface tension, which are interactions between water molecules. Um, an example of cohesion, you ever spilled something and wicked it up with a paper towel, right? Paper towel is made of wood pulp, and wood pulp is made of cellulose, and cellulose is made of carbohydrates, which we know are polar, right? Well, what do polar things do? They hook up, right? They get together. And the result is that when water molecules associate with the wood pulp in the paper towel, other water molecules associate with the water molecule that associates with the paper towel, and you suck up the entire spill, right? Surface tension is just the attraction of water molecules more strongly to themselves than to the gas or air above it. And that means there's a slight inward pulling force that can support the weight of certain organisms, like water striders, okay? It can cause the moist sacs of air in the lungs to collapse. The way we overcome that in the lungs is to produce something called surfactant, which is a detergent-like secretion that breaks hydrogen bonding and allows the lungs to expand and contract when you breathe in and out, okay? The same way a wet paper sack, if you've squeezed all the air out of it, would be hard to inflate. But if you were to put it in soapy water, you could inflate it and deflate it relatively easily, okay? Adhesion is just the attraction between water molecules and a substance other than water, okay? Cohesion and adhesion are both at work when we're talking about things like mopping up a spill, okay? Water can also give off or take up a lot of heat without changing its temperature significantly, okay? And it, as a result, can stabilize body temperature, okay? The heat of vaporization is the amount of heat required for release of molecules from a liquid to a gas phase, while the heat of fusion is the amount of heat absorbed or given off, rather, when you go from a liquid to a solid, okay? So this is how, for instance, sweat cools the body, right? When liquid water and sweat turns from a liquid to a gas, it takes energy with it. That cools the surfaces that the water was on, that the sweat was on. That cools the blood, and that in turn cools the body, okay? And we talked about the fact that it was also a universal solvent, okay? Okay. Two terms that we want to be familiar with are hydrophobic and hydrophilic, all right? A hydrophilic substance dissolves easily in water, and a hydrophobic one does not, okay? You could think of hydrophobic stuff as greasy, if you like, okay? And you could think of hydrophilic stuff as things that you normally easily dissolve in water, things like carbohydrates, like sugars, or salt crystals, okay, are all examples of things that are hydrophilic, okay? So that's the meaning of the term, right? Phobia means afraid of, right? So when we talk about a big molecule, right, like let's say a protein, you can have regions of that molecule that are hydrophobic, regions that are hydrophilic, and regions that are charged. And one of the things that drives the association of different parts of a long protein that's a chain of units called amino acids, one of the things that drives the ability of that long chain to assume a particular shape are these of interactions, right? Greasy stuff getting with greasy stuff, polar or charged stuff getting with polar or charged stuff, okay? And that's all, again, second law of thermodynamics. That system, that protein, is taking on the shape that requires the least energy to maintain, okay? Substances that partially dissolve in water are called amphiphatic. They'll have a polar or charged portion, and they'll have a nonpolar part, okay? An example is hand soap or phospholipids, right? Part of the phospholipid is charged or polar, and part of the phospholipid is nonpolar. So in water, a phospholipid is going to arrange itself in a way that the charged regions are in contact with the water and the uncharged regions are in contact with each other, which means they can either form a bubble with the inside being hydrophobic in water, or they can form a bilayer where you've got two layers of phospholipid and the interior is hydrophobic, okay? This is, for instance, why you can get greasy stuff off of your dishes and your hands using soap, right? We can use a little local history here to illustrate, okay? Back before we were called the Queen City, Cincinnati used to be known as Porkopolis, all right? And the reason was that we're on the Ohio River, and all the pork bellies would come up on barges, and then in the city of Cincinnati, we would process them and make all the good stuff you can make with pigs, like ribs and pork chops and bacon and everything else, right? And then what did you have left over when you were all done with that process? You had tons and tons of pig fat, right? Well, a very clever chemist understood that if you mix pig fat with lye, sodium hydroxide, which is a powerful base, you make something that is extremely useful in clinical and industrial hygiene. You make soap, all right? That's why if you've ever driven past a rendering factory where they make soap, it smells like soapy pork, okay? And so that was the foundation of a large industry in Cincinnati, which you may be familiar with, known as P&G, okay? You can see the different interactions with water here, right? Hydrophilic interactions, hydrophobic interactions, amphiphatic interactions, okay? All slightly different, okay? Water is a neutral solvent, but it can spontaneously ionize to form a hydronium ion and a hydroxide ion, but that doesn't happen at a great rate, okay? The reason we're interested in that is because it allows us to ascribe a property to water called pH, okay? And pH is just a measure of the concentration of protons that are in an aqueous solution, a solution containing water, all right? An acid is any compound that spits out protons into water, increasing the proton concentration and reducing the pH. Whereas a base is anything that does the reverse, picks up the protons from the spontaneous ionization of water, reduces the proton concentration, and raises the pH, okay? So that's what a base is, a proton acceptor, all right? Examples of acids include hydrochloric acid and carbonic acid, okay? And examples of bases include things like ammonia and urea and really anything containing nitrogen in a living system. Sodium hydroxide is an example of a strong base, okay? So we use pH as a way to determine what the proton concentration of a solution is, all right? And pH is a definite mathematical operation, okay? pH means the opposite of the base 10 log of the molar concentration of protons in the solution, okay? So if a solution has a proton concentration of 1 times 10 to the minus 3 molar, which is the number of moles per liter of solution, okay? Then if you take the log of that, you'll get -3, and the opposite of -3 is 3, okay? The pH of something that's 10 to the minus 6 in protons would be 6, and so forth, okay? There's a law that always applies in water, which is that pOH plus pH equals 14, okay? So if the pH of a solution is 8, the pOH is 7. Well, you might ask, well, what does pOH mean? Well, that's just the concentration of hydroxide ions in water, okay? And so you can go from pH to molar concentration and from molar concentration to pH of protons very easily, right? If you have something that's pH 5, the molar concentration of protons in that solution is 1 times 10 to the minus 5, okay? If you have a solution that's 1 times 10 to the minus 2 in protons, then the pH is 2, and so on, okay? So any solution that is pH neutral will have a pH of 7. Any solution that's acidic will have a pH less than 7, and any one that's basic will have a pH of greater than 7. And you can see here on the pH scale how that works, right? As we go up, the concentration of protons goes up and the pH goes down. As we go down, the concentration of protons goes down and the pH goes up, okay? So very few protons down here, very many protons up here. Okay, great. Why do we care? Well, we care because if you change the pH of a solution, right, you can damage the workhorses of life, which are called proteins, okay? And if you do that, the jobs that those proteins do will stop, and those cells will die. So the body works very hard to try to maintain the pH of your body fluids in most areas between 6.35 and 6.45. And it does that using 3 different body systems: a urinary system, the respiratory system, and your body's buffer systems, okay? So how does that work? Well, if your body pH gets too acidic, then you're going to make an acidic urine, okay? If your body pH gets too acidic, then you're going to breathe harder and faster. And the reason for that is to get rid of more carbon dioxide, because carbon dioxide forms acids in solution, okay? And if your body pH gets acidic, what your body's buffers will do is convert those acid molecules into weaker acid molecules, and the result is that the pH will go back up, okay? The definition of a buffer is a compound that can convert strong acids, which come apart completely in solution and change the pH big time, into weak acids, which don't so much. And it also changes strong bases, which suck up lots of protons and raise the pH, into weak bases, which don't do that so much, okay? And so buffer systems will work up to a point, right? If you throw too much acid or too much base into a buffer system, you'll overload it, and then the pH will shift dramatically, right? But if you stay away from those conditions, you'll avoid that, and the body will be able to continue to function, okay? Neutralization is just what happens when you throw an acid and a base together. You want to do that tonight, go home and get a glass and put it in the sink and put about, fill it about 1/4 of the way full with vinegar, okay? And then find some baking soda. Baking soda is a base, okay? Sodium bicarbonate. And then throw that into the vinegar and watch the neutralization reaction. It'll foam and fizz, and it'll give off a gas, okay? And that gas is carbon dioxide, right? And you'll form water, and you'll form a neutral salt, okay? Same thing that happens when you throw sodium hydroxide in with hydrochloric acid, okay? You form water and sodium chloride, okay? All right, we'll bump out here, okay? And we'll pick up the back end of this on Thursday, and I will see my Tuesday section at 6:45, okay? And we're going to begin with the idea of a mixture, all right? A mixture comes from combining two or more substances together. Now, sometimes one substance will dissolve in the other. The substance that dissolves is called the solute, and what does the dissolving is called the solvent. Sometimes they won't dissolve in each other, okay? The way to tell if you have one substance dissolved in another in a water-based solution is if it's clear, okay? Now, when you mix, the substances are not chemically changed, and you can separate them by physical means. For instance, if you added salt to a glass of water and stirred it up, and we wanted to get the salt and the water back out, we could do something called distillation, where we would take the salt water and we would boil it, and we could condense the steam that would then be the pure liquid water. What would be left behind in the boiled container would be the salt crystals, okay? There are other types of mixtures that are not solutions. There are suspensions, there are colloids, okay? And they have different properties, okay? They can be separated by different means. An example of a suspension is material larger than a millimeter mixed with water. For example, blood cells in whole blood are essentially a mix of liquid called plasma, which is mostly water, and formed elements, which are red and white blood cells and platelets. Okay, sand and water is another example of a suspension. What will happen is that if you let a suspension sit for long enough, the suspended material will eventually settle out in the bottom. Okay, for instance, if you mix sand with water and then you just wait long enough, the sand will settle to the bottom of the container and the water will stay on the top. The same would be true with whole blood. Okay, a colloid's different. A colloid has smaller particles than a suspension does, but they're larger than the solution particles, but they remain mixed upon standing, okay? But a colloid will scatter light, okay? An example of a colloid is Jello, okay? After you make the Jello, you've got proteins that are suspended in water, okay? And they actually form a semi-solid colloid mixture, all right? But upon standing, the proteins don't settle out, okay? A solution's a different deal, okay? In a solution, you have a solute that dissolves in a solvent and does not settle out, okay? It won't scatter light, it's clear, okay? Examples include sugar and salt water and blood plasma, not whole blood, but blood plasma. And then there's a suspension category called an emulsion, where you mix two things together that are chemically different in terms of their polarity, such as oil and water, or a bottle of Italian salad dressing, right? And what will happen when you mix those things is that they'll stay suspended for a short time, but upon standing, because of the second law of thermodynamics, the oil will separate out and the water will form its own volume, okay? So you'll see two distinct layers. Usually the oil is going to be on the top, right? So you can see here some examples of suspensions, colloids, solutions, emulsions. We have all of these in the human body, right? Blood is a suspension, plasma is a colloid, emulsions. An example of that would be the fat in our diet mixing with digestive secretions. Okay. Question. Go to click on the link and then go to today's date on the drop down and you'll find it. Okay. Yeah. Expressions of concentration include mass per unit volume and mass per volume percent. Okay. Mass per unit volume is always expressed as um, generally grams per liter, okay? Mass volume percent would be grams per 100 milliliters, okay? Those are general expressions. Now, there's another expression of concentration, which is a mass percent, and that would be the amount of solid material in grams per 100 mil of solution. An example of that, if you wanted to make a 10% solution of sodium chloride, all right, you would mix 10 grams of sodium chloride in a total volume of 100 mils. Okay, and once that went clear, that would be a 10% solution. Okay, you can have volume percents as well. You can mix a certain volume of something with another volume of something else, and it's mils per total milliliters of solution that would give you the percent. So if you say we're doing those beverage drops that you get in the grocery store where you can flavor things like water, okay? Maybe you take, let's make it easy. Let's say 1 ml of those beverage drops in 100 ml of solution, and you mix it. That would be a 1% volume percent solution, okay? Percent always means per 100. Molarity is the moles of solute per liter of solution, okay? And remember that a mole is nothing more than a count, okay? The mole is a certain count of molecules of a particular element or compound, and that number is 6.02 times 10 to the 23rd, okay? And the number of moles per solution is the molarity, okay? It can change with temperature because volume expands when temperature goes up, but it's more easily measured than molality, which is moles of solute per kilograms of solvent, which does not change with temperature, okay? But molar solutions are what you see most often. Molarity can be expressed as molar solutions, millimolar solutions, micromolar solutions, okay? Remember those prefixes are all powers of 10, right? Milli is 10 to the minus 3, micro is 10 to the minus 6, and so on, okay? An osmole is the unit of measurement for the number of particles in a solution. And what happens here is when you throw some substances into water, some will dissolve and come apart, and some will simply dissolve, okay? If it's a organic covalent compound, it's just going to dissolve, okay? So the osmolarity and the molarity are the same thing. But if it's an ionic compound, what will happen is that the osmolarity will generally be higher than the molarity, okay? Because you're going to generate more particles per unit volume when something like calcium chloride comes apart, CaCl2, than you would if you were to throw the same number of molecules of something like glucose in there, okay? And it's a measurement of the osmotic pressure of the solution, the ability of that solution to pull water towards it if there is pure water around it in contact with it, okay? So it's the number of, osmolarity is the number of particles in a liter of solution, while osmolality is the number of particles in a kilogram of water, okay? We've talked about what a mole is. It's just a count, like a dozen is 12, or a pair is 2, okay? And it's 6.02 times 10 to the 23rd of whatever we're talking about. So a mole of carbon, we know, weighs 12.06 grams. We know how many molecules are in that, 6.02 times 10 to the 23rd. A mole of something larger would weigh more, okay? Like, let's say, a mole of bicycles, all right, would probably weigh close to a ton or more, okay? To find molecular mass, you multiply the number of units of each element by the atomic mass and add the totals up, okay? So, for example, okay, water is H2O, okay? Oxygen has an atomic weight of 16, hydrogen has an atomic weight of 1, okay? So what is the molar mass of water? It's 18 grams per mole of water, okay? That is what we call the molecular weight or the formula weight of that compound, all right? Remember that every element has isotopes in it, so sometimes what you end up with is a little bit heavier than what you would expect. Okay? Now, macromolecules are a class of polymers in the body that are made up of repeating chemical units, okay? Examples include complex carbohydrates, DNA and RNA, protein, and to some extent, you could even argue fatty acids, okay? The main components are always going to have carbon, hydrogen, and oxygen. Remember that carbon is the linchpin of organic molecules because it can form rings and chains with itself, and other elements can't do that very well. And you may also occasionally see nitrogen, phosphorus, or sulfur in some of these polymers, all right? Hydrocarbons only contain carbon and hydrogen, but you'll run into biological macromolecules that have functional groups on them, okay, which are collections of atoms that provide certain chemical characteristics to the large molecule, okay? Examples of functional groups include hydroxyl or OH groups, amino or NH3 groups, carboxyl groups, which are COOH, okay? And there can even be phosphate groups on some of these things, PO4, all right? So some of these functional groups will be polar, some will be charged, and some will have an opposite charge, all right? And that will govern their interactions in living systems. That will govern how they come together and talk to each other, okay? We talked about the fact that polymers are molecules that are made of monomers that occur in repeating units, okay? One polymer, another polymer, another polymer, okay? Carbohydrates are polymers of monosaccharides, sugar monomers. Nucleic acids are polymers of chemical units called nucleotides, and proteins are polymers of chemical units called amino acids, okay? When we assemble these big chains, we use something called dehydration synthesis, which is basically the removal of a water molecule between two monomers to create a new connection between them, okay? For instance, you can create a disaccharide from two monosaccharides with a dehydration synthesis reaction. These reactions are termed anabolic reactions because they tend to build large molecules from smaller pieces, and that requires an energy source from some other chemical reaction. And that usually comes from a molecule called ATP. Okay? Hydrolysis is reverse. Okay? In hydrolysis, what happens is we take a large chain of something and we use a water molecule to cut those connections and release pieces of the chain. Okay? And those reactions are generally going to produce energy instead of yield them. So the energy to perform these kinds of reactions comes from these kinds of reactions, okay? These kinds of reactions are part of what we use to make ATP, okay? And these kind of reactions are what we use to build the pieces of the human body, okay? So, our next class of molecules are the lipids, all right? Now, lipids are unique because they are hydrophobic, meaning water-fearing, or they don't like to associate with water or anything polar, really. Okay, they just don't dig it because of the second law of thermodynamics. Because they don't have an unequal distribution of electrons across their surface, They don't have a positive and a negative end to them, which means they don't want to associate with things that do have a positive and a negative end to it. And those would be things like ionic compounds, which are made of cations and anions, and polar compounds, which contain electronegative atoms like nitrogen and sulfur and phosphorus and so on. Okay? The classes of lipids include triglycerides and phospholipids and steroids and eicosanoids. Okay? They all look a little different. Triglycerides are used for long-term energy storage, and they're made from glycerol and fatty acids. Okay? A fatty acid has a carboxylic acid functional group at one end, and then a long hydrocarbon chain coming off the back. Okay? So it's high in calories because it has a lot of carbon-hydrogen bonds. Okay? Saturated fatty acids have the maximum number of carbon-hydrogen bonds, and so they have the maximum number of calories. Unsaturated fatty acids are going to have double bonds between carbon atoms, and that's going to result in fewer carbon-hydrogen bonds and fewer calories. And then polyunsaturated fatty acids have two or more double bonds in them and have even fewer calories. Okay? Where are triglycerides stored? They're stored in a type of connective tissue that's called adipose tissue, which is basically an adipocyte, a fat cell, with a big droplet of fat in the middle, and the nucleus and the cytoplasm push to one side. And it's basically a fuel storage tissue. Okay? It also pads and protects our organs, insulates us so we don't lose a lot of body heat. Okay? And also obviously is a fuel storage depot. Okay? Lipogenesis is the production of triglyceride, and you're taking in more calories than you're burning. And lipolysis is the breakdown of triglycerides when you're burning more calories than you're taking in. Okay? You can see an example of a triglyceride here. Why is it called tri? Because you got three fatty acids. There's one, there's another, there's another. Okay? It doesn't have to be these particular three fatty acids. It can be any of a combination of any of the fatty acids that are out there. Okay? You could have a triglyceride that has polyunsaturates at all three positions, or saturates at all three positions. Okay? They're all different types of triglycerides. But you can see here that we hook the fatty acids to the carbohydrate glycerol by a dehydration synthesis reaction. We remove a water molecule from each of these component parts, and we form a new connection between the fatty acid and the glycerol that is pretty strong. Okay? And that is, again, an anabolic or energy consuming reaction. And then we store this in our fat in our body. Okay? But look at all those carbon-hydrogen bonds. There's tons of them. And as a result, there's lots of calories in here. And because it's mostly hydrophobic, the part that's hydrophobic is the part here that's not shaded. Okay? It's going to tend to associate with itself and squeeze out any water. And that means you can store a lot of calories in a very tiny volume. And that means that we have the ability, in the event that we don't have much to eat, to live off of this calorie reserve for a while until we find another food source. And our body's tendency to do that is the result, again, of evolution. Okay? You have to think back to when human life wasn't like it is now. Okay? We used to live in caves, and we used to eat in an irregular fashion, right? We would live in the cave, and we would look out of the cave, and then when something would walk past the cave, we'd run out, kill it, and eat it. Okay? Well, that might happen very frequently in a particular year or month, or sometimes it might happen very rarely. In order to survive, we had to be selected for fat storage so that we could live off of our body reserves long enough to get to the next meal, which means we would live long enough to breed and pass those traits, those fat storing traits, on to our children. Okay, so this is why now one of the big problems in Western cultures is obesity, because we have a diet that's high in calories and low in satisfaction. We call that satiety. So it's very easy to eat a lot of calories and then not realize that you've eaten them because you don't feel full. And the result is that you pack on the excess pounds in the form of body fat. Okay? Now, there is another piece to this molecule. This area up here where the glycerol is polar. And so it can associate with water. All right? So in a triglyceride, this end that's shaded is going to be poking out towards the water or the cytoplasm, and then this part's going to be tucked in the interior. Because again, the second law of thermodynamics states that like gets with like, right? Nonpolar stuff gets with nonpolar stuff, and polar stuff gets with polar stuff. Okay? Now, phospholipid is a modified lipid. Triglyceride essentially is the starting material for phospholipid. And what we do to make a phospholipid is that we strip off one of the fatty acids and then we add a phosphate group and then usually some sort of an amino group to the carbon that had the fatty acid removed from it. And so we generate something called a hydrophilic head in the molecule. So one part of the molecule is very much going to want to associate with water because it has a charge on it, right? While the rest of the molecule, those fatty acid tails, are going to want to associate with each other, and so they tend to tuck with other fatty acid tails away from the water, okay? This is the building block of cell membranes, and it forms something called a semi-permeable barrier, meaning that the material that goes in and out of the living cell isn't just anything, all right? It has to have certain properties in order to pass through that barrier, and if it doesn't have those properties, in order to get in and out of the cell, it's going to need a special gateway or tunnel or pump, and those are usually made out of proteins, okay, that are stuck in the membrane. Steroids are another type of lipid, and they're made up of a fused ring system that's mostly carbon and hydrogen, and so it's hydrophobic. Steroids can serve as chemical signals called hormones. They're part of cholesterol, which is used for bile salts in the body to emulsify our fat in our diet. So that's kind of like a detergent. It's also an important mediator of what we call membrane fluidity. You can stick cholesterol in cell membranes and you can control how much the phospholipids move around. So it acts kind of like a doorstop, okay? And eicosanoids are another class. They're made up of fatty acids that are modified so that one end has a ring in it. The ring can be, it's usually a five-membered ring, five-sided ring. That can be made from arachidonic acid, which is found in cell membranes, and they act as chemical signals. They're important in controlling inflammation and nervous system communication. The classes include prostaglandins, prostacyclins, thromboxanes, and leukotrienes. Okay? Most animal fat is going to be saturated fat. Okay? Think of Crisco or think of butter. Okay? So it's going to be a solid at room temperature, mostly. Vegetable fats are unsaturated. They have double bonds in their fatty acid tails. And so those fatty acid tails don't stack quite as well. They kind of move around a little bit because the double bonds make kinks in the chain. And so they tend to be liquids, and we call those oils. And they're generally healthier to consume because they have fewer calories in them, because they have fewer carbon-hydrogen bonds. We can turn them into saturated fats through a process called hydrogenation, and that produces the type of fat that we use in snack foods. Okay, so if you go to the vending machine and you get some Pringles or combos or whatever, there's probably some trans fat in there. Now, the trans fat is used in those products so that the shelf life is longer. Okay, it's not a plot to make you unhealthy. It's just a way to keep from having to change out the inventory every 2 days. Okay, so the trick with eating trans fat is to realize that you don't want to eat too much of it. Okay, and you know what your limit is. The trans fats are listed on the package so that you can determine whether you want to eat that snack or not in order to stay healthy. Okay, the reason that trans fats and saturated fats promote heart attack and stroke is because they increase the amount of bad cholesterol and bad triglycerides in our blood, and that can lead to a condition called atherosclerosis, where you get plaques that collect on your arteries, and that slows down blood flow, and that raises your blood pressure, and that can cause you to rupture capillary beds. If that happens in the brain, that's a stroke. If it happens in the heart, that's a heart attack. It also causes blood flow through those constricted areas to slow down, and the result of that is that the blood will tend to clot. And if the blood clots, then that clot can jam in a tiny vessel like a capillary and cut off blood flow to everything downstream, and those tissues can die. And in the brain, that would be a stroke, and in the heart, that could cause a heart attack. Okay? Carbohydrates are an organic molecule that always have the chemical formula chapt02 subscript N, okay? Which means what? Well, if a carbohydrate has 6 carbons in it, the chemical formula is going to be C6H12O6. If it has 5 carbons in it, it's going to be C5H10O5. Okay. What this means is that there's a lot of electronegative atoms in a carbohydrate, which means it's a polar molecule, which means it's going to dissolve in water. Okay. Unless it's very, very, very large. All right. In which case the solubility goes down a little bit. Okay. Monosaccharides are single ring sugars. Those are the monomers of complex carbohydrates. Disaccharides are double ring sugars, and polysaccharides are 3 or more. Okay, and you find all 3 of these in your diet. Okay, and you find all 3 of these in your body too. Okay, where they can be used for a variety of things. The most important reason we consume carbohydrates is energy, right? Because they contain a lot of carbon-hydrogen bonds, and that means we can make a lot of chemical energy from that. Glucose is a 6-carbon carbohydrate, and it's the most common monosaccharide in the body. It's blood sugar, and it supplies energy to cells. And we have to maintain the concentration in our blood very carefully. We don't want it to get too low or too high. Okay. Glycogen is made by liver and skeletal muscle, and it is a temporary storage form for glucose. Okay, glycogen is sometimes called animal starch, and it's what makes the white meat in a bucket of chicken taste sweeter than the dark meat. Okay, and starch itself is similar to glycogen, but it is found in plants, and it has fewer branches coming off the chain. But the way that the plant stores energy for itself, and it's also the way that we can get energy from plants to make energy for our bodies. Okay, so where do you find starch? In things like rice and corn and wheat and potatoes. Okay, it's the plant version of glycogen. All right, and we have the ability to digest glycogen and starch. Right, we can break it down into its monosaccharides, and we can load that into the blood, and from there it goes to the liver, and then from the liver we'll store it for a while, and then later we'll release it into the body so that the tissues can get it from the blood and use it to make energy. Okay, So there you can see what glucose looks like and what glycogen looks like, and the two processes that build up the glycogen and tear it down. And those processes usually happen in different locations and in different tissues so that they don't interfere with each other. Okay. Other types of carbohydrates include things like galactose and fructose, which are isomers of glucose, meaning they have the same chemical composition, right? They have the same building blocks, but the building blocks are attached to each other in a different order. And then 5-carbon monosaccharides like ribose, which is part of the backbone of RNA, and deoxyribose, which is part of the backbone of DNA. Disaccharides are just simple sugars connected to each other. Examples include sucrose, which you know is table sugar, which is a combination of fructose and glucose, lactose, which is galactose connected to glucose, and maltose, which is two glucoses attached to each other. Okay? And all of these are made and then broken down in different locations by different tissues in the body. Okay? Polysaccharides, 3 or more sugars attached to each other. Glycogen is the most common in animals. Starch and cellulose is in plants. And we've already talked about starch being a major nutrient in our diet, right? Cellulose is a type of polymer made from glucose that we can't digest because we don't have the correct enzymes to break the connections between the glucose molecules in cellulose. And so we call that fiber. You know it better as wood, okay, or paper. And it goes right through the body without providing any calories. And this is one of the ways that you can reduce your calorie intake, right? Is by including a lot of fiber in your diet, you're able to make yourself feel full, but at the same time, not take in as many calories because all that stuff goes right to the colon and then right out with your feces. You can see some other carbohydrates here, okay? And you can see how they're connected to each other, right? Those are called glycosidic bonds down here, those little connections between these single ring sugars, right? All right. Nucleic acids, all right, are essentially information molecules, okay? The two kinds are DNA and RNA, all right? Are built from nucleotides that are connected to each other one after the other, and the monomers are covalently linked through what are called diester bonds, all right? The kind of information they carry is called genetic information, okay? So there are areas in the DNA of nucleotides hooked together one after the other that contain instructions that are used to build the proteins in the body that do the work of life, okay? And so when we need to build those proteins, we have special tools, special proteins that go in and find those stretches of DNA, and they photocopy it into an RNA molecule. And then that RNA molecule leaves where the DNA is located, which is the nucleus of the cell, and it moves out into the cytoplasm, where another particle in the cell called a ribosome uses those instructions to build the protein that's going to do the work, okay? And that's how information flows in living systems, from DNA to RNA to protein. You can see the parts of a nucleotide here, right? The nitrogenous base over here in green is the information part of the molecule. The sugar and the phosphate are part of the backbone, okay? And in DNA, there's a hydrogen at this position, and in RNA, there's a hydroxyl at this position. Okay, so this is a pentose sugar because it only has 5 carbons. Where are they? 1, 2, 3, 4, 5. Okay. In DNA, this part is tucked into the middle of something called a double helix, and this part runs along the outside, sort of like a double spine going up either edge of the doublets. Okay? 5 types of nitrogenous bases occur. Cytosine, uracil, and thymine are the pyrimidines. Uracil is only found in RNA, and thymine is only found in DNA. And then the purines are adenine and guanine, and those are found in both DNA and RNA. Okay? Nitrogenous bases with either group differ in the functional groups that are attached to the ring. You can see what they look like here. Okay? So the pyrimidines are the less complicated structures, and the purines are the more complicated ones. Okay? And you can see that there's a lot of nitrogen in here. And there's, as a result, a lot of potential for hydrogen bonding. Okay? So what I want to do next is show you a little bit about DNA and RNA. So let's take that opportunity now. We can just do that the easy way, right? Go here, and go here. There we go. There we go.
DNA and RNA are nucleic acids, polymers made of subunits called nucleotides. One difference between DNA and RNA is the type of sugar their nucleotides contain. DNA contains the sugar deoxyribose, while RNA contains the sugar ribose. Ribose has one more oxygen atom than deoxyribose. DNA and RNA are each composed of 4 different nucleotides, which differ in their nitrogenous bases. 3 of the 4 bases are the same in DNA and RNA: adenine, guanine, and cytosine. The 4th base in DNA is thymine. In RNA, it is uracil. The nitrogenous bases guanine and adenine each have 2 linked rings of atoms. They are called purines. Cytosine, thymine, and uracil each have a single ring, and these 3 bases are called pyrimidines. For convenience, the carbon atoms in a nucleotide sugars are numbered, beginning with the carbon atom bonded to the nitrogenous base, moving around the ring, and up to the carbon that is bonded to the phosphate group. The 1' carbon is bonded to the nitrogenous base, the 3' carbon to the next nucleotide, and the 5' carbon to the phosphate group. DNA and RNA are polynucleotides, long chains of nucleotides. Polynucleotides are always assembled in the 5' to 3' direction. A covalent bond forms between the carbon at the 3' position of a nucleotide and the phosphate group at the 5' position of the next nucleotide. RNA usually consists of a single polynucleotide chain. DNA, on the other hand, consists of 2 polynucleotide chains. The 2 DNA chains, or strands, are oriented in opposite directions and held together by hydrogen bonds between the nitrogenous bases on opposite strands. Because of their sizes, shapes, and arrangement of polar groups, the DNA bases form complementary pairs. Adenine pairs with thymine, and cytosine pairs with guanine. The two polynucleotides in DNA wind around each other to form the familiar double helix. The bases can be in any order, like the letters of the alphabet. However, the base sequence is significant. Sequences of bases called genes encode the instructions for the structure and function of an organism.
Okay. Let's pop back. I'm going to go here. Okay. So, you can see here the structure of DNA and RNA, right? In DNA, we have two strands that run in opposite directions, but the bases pair such that C always hydrogen bonds with G and T always hydrogen bonds with A, right? The reason for this structure is so the DNA can reproduce itself when new cells get made. When the double helix unwinds, the information in the old strand is used to guide the generation of the information in the new strand. And the result of that is that the information is preserved. And so the new cell has all the instructions it needs to build the proteins that allow it to survive, right? The RNA is just a single-stranded molecule, and it's like a temporary photocopy of a gene in the DNA, which simply is a stretch of the double helix that contains protein building instructions. Now, sometimes what happens is that in the generation of new DNA, you make a mistake, and those mistakes are called mutations. And mutations can have three outcomes, right? They could be beneficial, they could be hazardous, or they might not have any effect, okay? A beneficial mutation would be one that produces a characteristic in the organism that makes it more likely to survive and reproduce. A hazardous change, a bad change, is one that makes that less likely, and then a neutral change doesn't have any effect, okay? ATP is simply a nucleotide that serves as an energy source. Now, where is the energy in ATP? And the answer is that it's in the phosphate groups, all right? The phosphate groups are negatively charged, which means they repel each other. And so the covalent bonds that hold them together have a lot of power, a lot of energy in them. And when they get clipped, that energy that comes out can be trapped and used to do other work, okay? So this is a way to think of ATP is like gas in the tank for living systems, okay? This is where we get the fuel from, and it's ready to do the work right away, okay? The reason that we have to use ATP for energy is that the cells aren't set up to use anything other than ATP to do their work right away, all right? They can't directly take the energy, for instance, out of the sugar molecule and use that to build something. They have to pass it to ATP first. So a good way to think of this is sort of like the gas in your car, right? The gas that you put in your car is the fuel that lets your car do things that it otherwise couldn't do, like drive up a hill, okay? The energy in the gasoline is contained in the carbon-hydrogen bonds in the gasoline, and when that gasoline goes to the carburetor, it mixes with air that has oxygen in it, and the spark plug will make a little spark, and there'll be a little explosion inside your engine block, and that moves pistons up and down, and those pistons turn a crankshaft, and that eventually turns the wheels of your car, and then you go, okay? But where does gasoline come from? It comes from something called crude oil, which is a sticky fluid that comes out of the ground, And if you were to put crude oil in your gas tank, your car wouldn't run because it doesn't understand the energy in crude oil. It's not set up to deal with it. So what we do to make gasoline from crude oil is that we crack it. All right, we take that crude oil, which are basically long hydrocarbon molecules, and we bust those molecules into tinier pieces. And the piece in gasoline that makes your car go is called octane, and it's an 8-carbon hydrocarbon. All right, high octane fuel makes your car go far. Okay, so it's the same deal with ATP, right? The energy from the fuel molecules, which could be the fatty acids or the sugars that the cell takes in, gets moved over to ATP, and then from ATP, we can steal that energy and do work. Okay? All right. Proteins are a little bit different. All right? Proteins are the workhorses of all of life. Okay? And the way that proteins are able to do this, okay, if we jump real quick over here, is that they have building blocks called amino acids that look like this. Okay? Okay? Those are the amino acids that make up all the protein in our body. Okay? The ones that are shaded are called the essential amino acids, and we have to eat them in our diet in order to have them. The red ones are the charged amino acids, and so they have a collection of atoms called the R group on them that has a charge, either positive or negative, okay, at neutral pH. The polar amino acids have an R group that has an electronegative atom or two in it, and they tend to associate with water or each other, okay? And then the nonpolar amino acids don't have electronegative atoms in them, and they tend to associate with each other, okay? So when you build a protein, what you do is you hook these amino acids together in a particular order. Now, how do we know what order to hook them together in? Well, that comes from the information that comes from the DNA to the RNA, okay? Those are the magic instructions. So that's the recipe for building that particular protein, all right? So let's look at how the hookup takes place, and then we'll look at protein structure here.
Proteins are polymers of amino acid monomers. Every amino acid contains a central carbon atom bound to 1. An amino group, 2. A carboxylic acid group, 3. A hydrogen atom, and 4. A group that differs from one amino acid to another and is represented by the letter R. This dehydration synthesis reaction has created a protein consisting of 4 amino acid monomers.
Now, once you build that, you've generated something called the primary structure of the protein. And there's information in that primary structure that's going to let that protein take on a particular shape. All right? So let's see how that happens.
Each protein has a unique primary structure, a particular number and sequence of amino acids making up the polypeptide chain. 20 different amino acids are used to build proteins. Theoretically, the various amino acids could be linked in almost any sequence, forming an almost infinite variety of different proteins. This illustration shows some of the amino acids making up the primary structure of a protein. The structure of a single generalized amino acid is shown below. The main backbone of every amino acid is the same. This is what forms the backbone of the polypeptide chain. It is the R group, which projects out from the backbone, that makes each of the 20 kinds of amino acids unique. Different amino acids have different properties that affect the folding of a protein. Thus, primary structure ultimately determines the shape of a protein, which determines its function. In most proteins, parts of the polypeptide chain are coiled or folded, forming twists and corrugations. This is secondary structure. The turns and folds of secondary structure contribute to the protein's overall shape. One kind of secondary structure is the alpha helix, where the chain twists. Another is the pleated sheath, where the chain folds back on itself, or where two regions of the chain lie parallel to one another.
Secondary structure results from hydrogen bonding between atoms along the polypeptide backbone. Oxygen and nitrogen atoms along the backbone exert a stroll on electrons, giving them partial negative charges, and leaving nearby hydrogen atoms with partial positive charges. These negatively and positively charged atoms are attracted to one another at regular intervals along the chain, causing parts of the protein to twist or fold back upon itself.
Superimposed on primary and secondary structure is tertiary structure, irregular loops and folds that give the protein its overall three-dimensional shape. The irregular folding of tertiary structure results from interactions among the R groups of amino acids. Acidic and basic R groups ionize, and these positively and negatively charged groups may form ionic bonds. Polar forces also contribute to tertiary structure. Hydrophilic or polar R groups may hydrogen bond with one another or turn outward and hydrogen bond with the surrounding water. Hydrophobic, nonpolar R groups cluster on the inside of the protein away from water. Tertiary structure may be further stabilized by strong covalent bonds between sulfur atoms in certain R groups.
Okay. Kill that. Okay. The last part was quaternary structure. And in quaternary structure, what happens is that the amino acids, which have formed the primary, secondary, or tertiary structure, those chains form little shapes that can fit together like puzzle pieces and generate a functional protein that's made up of more than one polypeptide chain. Now, sometimes proteins need a little help in order to do their job. Generally, this help comes from, is available for things like enzymes, which promote chemical reactions. And these include prosthetic groups, such as heme, which is designed to help hemoglobin carry oxygen in the red blood cells, or coenzymes, which are vitamins that are used as tools by enzymes to do their work, or minerals like ions that can be used by these proteins to help them do their job. So you could think of these as little tools that certain proteins need in order to work. Now, sometimes what will happen to a protein is it'll find itself in conditions that it doesn't perform well in, and that will cause the change of the shape of the protein to a shape where it can't work, and that's called denaturation. All right. So the idea with denaturation is that Um, when the protein is working in the environment that it likes, which means the proper temperature, the proper pH, and the proper salt concentration, then it is going to form a shape that it allows it to do its job correctly. But when you change those conditions, then that shape is going to unravel, all right? And what you'll have is a non-functional protein. And this is why there are a lot of organ systems in the body designed to keep the body pH and the body temperature and the body fluid balance within a certain window so that these proteins can do their work, okay? Denaturation can usually be, or it can either be irreversible or reversible, okay? And it can be the result of changes in any of these factors, all right? So you can have pH change, you can have temperature change, you can have change in salt concentration, you can have change in the fluid balance, or you can even have chemicals that can denature the protein, all right? And all of that can be lethal to the cell, okay? It would be as if I went into your toolbox and bent all your tools, right? They wouldn't be useful anymore because they're in their wrong shape. And the result is they're useless to you, so you can't do a job with them. And for the cell, if you ruin its tools, it can't function at all, and so it's going to die, okay? And so that's why homeostasis is so critical, right? The maintenance of a constant, well, the maintenance of a body temperature within a correct range, body pH within a correct range, and all of those other conditions we talked about is important for the tools of life to do their job. And if we change those, then the tools of life can't work, and the result is that the life processes will stop. We'll die, okay? All right. That brings us to the end of this segment